did it, made the math kind of easy, so you really wouldn't need a calculator, but just so you would be able to go through and validate whether or not you understood the process on how to do this. So right now, I'm not going to ask for hands, but you probably know right now whether or not you understand how to do this process-wise, just going from place to place to place. So today, in this quiz, is primarily an opportunity to review the process. You might get different numbers, but the process, like any problem we do, you'll have different givens. But as long as you follow the process from the given to the asked for, step by step by step by step, every one of these problems, I won't say are simple, but again, if you know the process, that makes it much simpler, right? If you know how to walk through the diagram, doing it the way that I taught you. So the question asks that if 80 grams of AB2, process-wise, if 80 grams of AB2, what am I going to do first, given that? I mean, I already have the reaction equation, right? But if the question says, if 80 grams of AB2, according to the process I've given you, go to the molecule where they state, AB2, how much? 80 grams. Again, I kept it easy with no decimals, nice round numbers. Okay. So 80 grams. Remember, the space right below the reaction equation is reserved for mass. In the future, it also can be reserved for density. We'll talk about that later. That's another step in this whole process. But for right now, the space just below each of the molecules is for the mass given or asked for of that reactant or product. So if 80 grams of AB2 reacts with excess C, how do I note excess? What's the symbology we use for excess? Plus sign. I just said plus sign. I tend to circle it. What does that mean if it's in excess? You've got plenty of it, right? Again, some of it, I see your mouth, your lips moving, you're a distance from me, whether it's because you're speaking softly, because that mini fridge is really loud, because I've got like 3,000 hours flying helicopters. I'm not sure, or I'm 50, soon to be 53. I don't know which one it is, but if you say the right thing and I don't hear you, it's a combination of all those things, probably that's keeping me from hearing you. So, in excess means that all of this is going to be used up. This is the limiting reactant. This is the key that controls how much of this is used and how much of everything is produced. The key is in the limiting reactant, and since this is in excess, this is the master, this is the controller. All right, so if 80 grams of AB2 reacts with excess C, how many grams of each product are formed? The products you need to know on the product side of the reaction arrow, how many grams of each are formed. So that's my setup just from the word problem. This is where I'm going to go to first. Okay. 80 grams in excess produces how many grams of each product? So I know by process, I'm going to draw a vertical line between or underneath the stoichiometric coefficients of the molecules in question. Let's just look at the formation of BC first. Okay. I'm looking just at, given 80 grams of AB2 in excess C, how many grams of BC are formed? Generically, every time you do this, we're going to be moving from grams to moles to moles to grams. You could go right now and just write here moles of AB2. And you could write down here moles of BC. Because I know I've got to use stoichiometry to move from moles to moles. Remember, I can't move from grams to grams. I can only go from moles to moles. So I have to go through a process of translating grams to moles, use stoichiometry to go from moles to moles, and then use the process to go from moles back to grams. It means there's some process that has to take place between mass to moles and between moles to mass. So also generically, every time you do this, you can go ahead and write down your reaction arrow. Your flow arrow. You're going from here, from 80 grams to how many grams, which means I'm going to travel in this direction, right? Traveling from my given to my asked for. And I know every time I move from grams to moles, my process is going to, well, both from grams to moles and moles to grams, there's a key that helps me on translation, right? What is that key? My molar mass. My molar mass of the molecule in question. So I need the molar mass of the first molecule, AB2. You're given that A is 10 AMU and B is 15 AMU. Okay. So AB2 would be 40 AMU per molecule, right? 40 AMU per molecule could also be written as what? 40 grams per mole. 40 grams per mole. And in process, as I go from grams to moles in this direction going down, what is my operation going to be? Pardon? Division. I'm going to divide. So I'm going to go from 80 divided by 40 gives me, pardon? 2 moles. Mathematically, that's 80 grams of AB2 times 40 grams of AB2 for 1 mole of AB2 equals 2 moles of AB2. In your book, you would see this conversion factor used. That conversion factor is highlighted in this process by going from this divided by this takes me here. Again, I'm just walking from point A all the way around to point B. To go from here to here, I divide by the molar mass of that molecule. Now we need to go from moles of AB2. How does that correlate to the moles of BC? Stoichiometric relationship, which is what? 1, remember? Coefficient here is 1, 2, 2. It's a relationship of 1 to 2 using the stoichiometric coefficients. Moving in the direction from left to right, what does my multiple become? 2. It's 2 over 1. Remember, graphically, the first number you hit gets driven to the denominator of the multiple. So my multiple is 2 over 1. What does that formally represent? Well, for every 2 moles of BC, that relates to 1 mole of AB2. So 2 moles of AB2 times 2 moles BC over 1 mole of AB2. Do you see the math? This times this, my units cancel, and I'm left with 4 moles of BC. I wasn't asked for moles of BC, however. I was asked for grams of BC. So I again need to convert from moles to grams. The key is molar mass, the molar mass of the molecule in question, BC. BC, well, B was given as 15 AMU and C was 20 AMU, so it's 35 AMU. 35 AMU per molecule or 35 grams per mole. Okay? The operation is multiplication. Moles times grams per mole gives me grams. Remember, if you get confused graphically, when you go from moles to grams, you're going up, and generally multiplication is easier conceptually than division. They're the inverse of each other, but I know we think in terms of multiplication first, so up is multiplication. 4 times 35. So what is the mass of molecule BC? How much is formed? 140. 4 times 35, or 140 grams. Okay. 140 grams of BC. Now, we were also asked for the grams of A. There's 2 ways I could do this. One way would be to relate AB2 directly to A and do it the same exact way, same exact flow, right? That would be valid. There's a second way that's equally as valid, and that is, now that I know how much of this is formed, I can relate this to this. Right? So if you were to just consider AB2 and A, you do the same thing. Draw a vertical line down, move all the way across, come up to A, and walk through each step just the way we did this time. Except over here, you would use molar mass of A. Or, because we've solved this step, we can now take here and go to this point. We could relate these 2 to 1. 2 to 1. And we know that we have 4 moles of BC. So how many moles of A are produced? What's the multiple? As we move from left to right, we hit 2 to 1, and our multiple is 1/2, which means for every 1 mole of A, we require 2 moles of BC. We're given 4 moles of BC. How many moles of A are produced? 2 moles. The shortest way of figuring out how many moles you have over here is to look up and notice that AB and A are in a 1-to-1 relationship. We started with 2, so we must produce 2. But if you did the math and walked it around, it'll be equally true. You just got there a different way. Okay. So 2 moles of A are produced when 4 moles of BC are produced. What is the mass of A that's produced? Well, A has a molar mass of 10 grams per mole. So 2 moles times 10 grams per mole is 20 grams of A. If I were to ask you right now, how many grams of C were used in this reaction? How could you solve that real quickly?
It's 80.
Correct, it's 80 grams. And you know by conservation of mass, whatever the mass is on this side of the reaction arrow has to be equal to that side of the reaction arrow, right? This side of the reaction arrow is 160 grams. This side is 80 grams plus whatever C was used. So C must be 80 grams. 80 and 80 is 160. 140 and 20 is 160. That is the first question in the quiz. Guys, your chatterbox is over there today. What's up?
I was asking if I needed it.
Oh,
I said, I am now. So,
you got a what?
L.
An L?
L. That's not.
Second question. If 2 liters of AB2, okay, I'm going to do this one top of the reaction arrow, just so I don't have to erase everything. But I'm going to go above rather than down so I can draw the line up. If 2 liters 2 liters of AB2 reacts with excess C. How many liters of each product are formed? Now remember, when you're going from liters to liters using Gilles-Sachs law, it's the same as from going to moles. Normally you would just put this down here and go, okay, so this many liters times something produces this many liters times this many liters. You don't have the vertical portion. We will later when we talk about densities and stuff like that, but for right now, the vertical portion, just comparing liters to liters, all we have to do is relate them stoichiometrically across. So how many liters of each of these are produced? Well, we have 2 liters of AB2 gas, and we're asked to say how many liters of BC gas are formed. What's the stoichiometric relationship there? 1 to 2, correct? So the multiple becomes 2, going from 1 to 2, left to right. 1 is driven down, same here, same numbers here, 2. So 2 liters of AB2 produces 4 liters of BC. How many liters of A are produced? We don't have a clue. Why not? It's not a gas. Gilles-Sachs only applies to gases. A is a liquid. So Gilles-Sachs law does not apply, and so we can't make any statement about the volume of A because it's not a gas. So the answer to that portion is, beats me. I can tell you how many moles we have, but I can't tell you how many liters that takes up because it's not a gas.
You tricked us on that one.
Pardon?
You tricked us on that.
No, well, if you consider the fact that every time I've talked about it, I've said, you can't do this. This is the most common mistake. Some of you will do this. If that's being tricky, you know, I asked you to bring, you brought something to write with too, and just kind of knew that was coming, right? You will be asked to find the volume of a product that is not a gas. And your answer will be, can't solve it. Need more information. All right. Let's go to page 301. Another empirical formula question. Expect a much briefer quiz tomorrow on empirical formulas, okay? Some aspect of empirical formulas. Again, this is the same process that you will use for this type of a question, no matter what the numbers are. I use generic makeup elements A, B, and C. That's why I wanted you to know this is not carbon. This is element C, element A, element B, element C, element D, so on. But this exact same process, given a mass, solve for mass, given moles, solve for mass, given mass, solve for moles, it's the same process. Whether it's products, reactants, and we are on 301, no matter what, the same exact process. So if you understand this process, you can pace yourself and work yourself through any stoichiometry problem, that's this part, and any conversion between mass and moles, which are these parts, up and down. It's all in that flow diagram right there. And so a quiz question could be, given this generic formula, or given this reaction equation, don't solve for anything, just tell me what goes in each place. Like the mass of the molecule, the mass of the given is here. The molar mass of the given is here. The moles of the given is here. The stoichiometric relationship is here. The moles of the S4 is here. The molar mass of the S4 is here. The mass of the result is here. The S4 is here. And use that basic diagram, that basic flow on every problem that asks for those things. Okay. So, example 811. We did, I think the other example on the other page, 810, last time, talking about glucose and water. Was that the one? Oh, that's CH2, the molecular mass. Glucose was earlier than that. All right. So compound's empirical formula is given as PO3. For me, I just read inside that's the empirical. It's just my shorthand for myself. Empirical. The empirical is PO3. Now, if a molecule has the empirical formula of PO3, which is, remember, P1O3, the one is implied, okay? If the empirical formula is PO3, then what could the molecular formula be? It could be PO3, right? The molecular could be the empirical. This times 1. So the empirical can always be the molecular, but it's not necessarily the molecular. So the molecular of PO3 empirical could be PO3. It could also be P2O6. Could also be P3O9. It could be P4O8. It could be P5O10. Excuse me. 6, 9, 12, 15, right? One more. It could be P6O18. All of these represent multiples of this initial empirical. You take the subscripts, times 1, times 2, times 3, times 4, times 5, times 6, and so on. Given that the empirical is PO3, if its molar mass is 158 grams, its molar mass is 158 grams, what is its molecular formula? What is its molecular formula? Two ways you can solve this. First one, let's go back and figure out what is the molecular formula of the empirical, PO3. Because since the molecular is going to be some multiple of the makeup of the empirical, the molecular mass of the molecular formula of the molecule itself has to be some multiple of the molar mass of the empirical. See that? This is twice as big as this, right? Twice as many components as this. Therefore, its mass is twice the mass of this. This is 3 times the mass of this. This is 4 times the mass of this. Get it? Okay. So what is the mass of PO3? So it's 1 phosphorus and 3 oxygens. Going to the periodic table. 30.973, I would assume in your book then they round that to 31. For phosphorus, and oxygen is 16. So the molar mass of PO3 is 31 plus 3 times 16. And that is equal to 79 AMU. It's also equal to 79 grams. It's grams per mole, AMUs per molecule, right? Two ways I can solve it. I need this information no matter what. I need to know the empirical formula, and I need to know the molar mass of the empirical formula. Given those 2 pieces of information, I can solve for what the actual molecular formula is by saying, oh, wait a minute, I'm told that the molecular formula is 158 grams. And I know that the empirical formula has a molecular mass of 79 grams. How many times bigger is my actual than the empirical? Two. If my molecule actually has a mass of 158 grams and my empirical molecule has a mass of 79 grams, my actual contains twice the components of the empirical. So I come over here and say, here's my empirical, double this and double this. What does it give me? P2O6. This is the molecular formula. Why? It's a ratio of the empirical, and it's double the mass, so it's 2 times the empirical. Not 2 times the empirical like this. That's just double the empirical, right? What we're doing is constructing one molecule that has twice as much mass. And so we double the subscripts. P2O6 is 2 times P1O3. The other way you could do it, if you completely go brain dead on that, right, is sit here and go, okay, it could be one of these. This would be 79. This would be 158. This would be, and add 79 to that, and add 79 to that, and add 79 to that, and pray that it's not P100O300, because it's going to take you a long time to get to that point, right? The quick way is to say, my actual divided by my empirical gives me a multiple of 2. If I take my empirical with a multiple of 2, P1O3 becomes P2O6. That has, and you might have to check yourself, compute the molecular mass of that formula and see if it matches what you were given. That's exactly what they do there on page 301, determining the formula for diphosphorus hexaoxide. Diphosphorus hexaoxide. Let's work through on your own. Let's see, 810, or are we going to the next one? Let's go on to the on your own, should be very similar to that. Let's work example 812, and this is the last structured component of the module. So we are technically done after we do this problem. I haven't looked at it yet, so walk me through it, okay? A sample of brown-colored gas decomposes into .34 grams of nitrogen and 5.34 grams of oxygen. Okay. Follow my process that I've used in stoichiometry up to this point. I go ahead and write down, we were given nitrogen and oxygen. When I decompose into the elemental forms, they're going to be N2 and O2 since they're both homonuclear diatomics. And we're given a mass of each that was produced. We don't know what this is. We can say right now that this is what? Some combination of nitrogen and oxygen, right? It's some combination of nitrogen and oxygen. So what is the empirical formula of this? What's its empirical formula? Well, we don't know what the subscripts are, but we do know it's some combination of nitrogen and oxygen. So X and Y are the variables. They're the subscripts of the nitrogen and the oxygen. We don't know yet what they are, but we know there's something. But 1 or greater than 1, right? Can't be 0, otherwise they wouldn't be up there in the first place. So we do have masses. Considering the module, what do you think we're going to do with the masses? Let's convert them, right? Let's convert them from masses to moles. But that's what we're really concerned about. Not how much matter we have, but how many pieces we have. How many pieces? Well, nitrogen, 2.34 grams. To go from mass to moles, what do I need to do? What's the operation going to be? It's going to be division, right? Going down is going to be division. And we're going to divide in both these cases by, the key is, the molar mass. And the molar mass of what? The molar mass of the product in question, the molecule in question. So it's going to be the molar mass of nitrogen and the molar mass of oxygen, which are 28 grams per mole and 32 grams per mole, respectively. When we do that, we do the math. So 2.34 divided by 28 and 5.34 divided by 32, the math tells us that we have 0.0836 moles of nitrogen and 0.167 moles of O2. That's how much was produced. I was given what was produced in grams, and I, using the molar mass, convert both of those into moles. So 2.34 grams is the same as 0.0386 moles of that gas. Now, look at this. Do you notice the relationship between these two things? Do you see any relationship between them, just by the numbers? Let me suggest this. As part of your process, look at these two numbers and figure out which one is the smallest. Hopefully you see that 0.0836 is smaller than 0.167. Divide them by the smallest of them. So look at all the products, divide by the smallest one. If I divide this by 0.0836, and I divide this one by 0.0836, what does the math resolve to? 1 to 2. My relationships of my products is that nitrogen and oxygen form in a molar proportion of 1 to 2. What do you think I do with those numbers 1 and 2? And since it's a 1, it's implied, so I can erase it. So my empirical formula, because it produces product of nitrogen and oxygen in proportion of 1 to 2, means that in the empirical, they're in that same proportion, 1 to 2.